Heavy oils are more difficult to recover from the subsurface reservoir than light oils. The definition of heavy oils is usually based on the API gravity or viscosity, and the definition is quite arbitrary, although there have been attempts to rationalize the definition based on viscosity, API gravity, and density. For many years, petroleum and heavy oil were very generally defined in terms of physical properties. For example, heavy oils were considered to be those crude oils that had gravity somewhat less than 20 API, generally falling into the API gravity range 10 to 15. For example, Cold Lake heavy crude oil has an API gravity equal to 12, and extra heavy oils, such as tar sand bitumen, usually have an API gravity in the range 5 to 10. Athabasca bitumen equals 8 API. Residua would vary depending on the temperature at which distillation was terminated, but usually vacuum residua are in the range 2 to 8 API. Hello my friends, welcome to my Energy Economist channel. We will talk about biological upgrading of heavy crudes in this video. Stay with me, then. Heavy oils have a much higher viscosity and lower API gravity than conventional petroleum, and primary recovery of these petroleum types usually requires thermal stimulation of the reservoir. The generic term heavy oil is often applied to a crude oil that has less than 20 API and usually, but not always, a sulfur content higher than 2% by weight. Further, in contrast to conventional crude oils, heavy oils are darker in color and may even be black. The term heavy oil has also been arbitrarily used to describe both the heavy oils that require thermal stimulation of recovery from the reservoir and the bitumen and bituminous sand formations from which the heavy bituminous material is recovered by mining operation. Extra heavy oils are materials that occur in the solid or near solid state and are generally incapable of free flow under reservoir conditions. The expected increase in the production of heavy and extra heavy crude oils has led oil companies to develop new technologies in order to improve their properties, as well as to facilitate their recovery and transportation. Chemical and thermal methods commonly used are expensive and troublesome, which together with the increasing environmental restrictions resulted in an increased interest in the application of biological treatments to reduce the viscosity and density of unconventional crude oils, as a cheaper and environmentally friendly alternative or as a complementary technology. For instance, solvents are usually employed to reduce the viscosity of heavy crude oils and help in their recovery and transportation. These chemical compounds could be replaced by biosurfactants, surface-active compounds synthesized by microorganisms, which can perform the same function and, due to their biological origin, are less toxic and more easily biodegradable, thus implying a greater environmental compatibility. Special attention has been paid to the biological upgrading of heavy and extra heavy crude oils, the goal of which is to improve their value and make them easier to produce, transport and process. The reactions that could improve the properties of heavy crude oils include cleavage of large aliphatic chains, aromatic rings, heterocycles, resins and asphaltene molecules into smaller compounds to reduce the average molecular weight of crude oil and, at the same time, modify their interactions with other molecules, resulting in the rearrangement of aggregates to liberate the smaller trapped molecules. As a result, the viscosity of the oil is reduced and its flow properties are improved, which enhances the mobility of crude oil through the reservoirs and the pipelines. Despite some promising results achieved in bioconversion of heavy oil fractions using different microorganisms, a limiting factor is that long incubation times are required, in most cases about 15 to 60 days or more. The bioconversion of crude oil's heaviest components, such as asphaltenes, using whole cells is difficult, due to their low solubility and low mass transfer rates in aqueous systems, where the microbial activity usually takes place, and the difficulty of their transportation across the cell membrane, which results in low transformation rates. Therefore, it is desirable the development of biotechnological processes that can upgrade heavy and extra heavy oils in a one-phase, non-aqueous system. Enzymes require less water than microorganisms to perform their catalytic activity. In this case, crude oil itself can act as a reaction matrix, thus avoiding or minimizing the addition of water, and consequently increasing the solubility and the bioavailability of hydrophobic substrates. The ability of enzymes of working in the absence of water or with very low amounts of water represents an advantage when compared with the use of microorganisms for crude oil upgrading. If you want to learn more about biological upgrading of heavy crudes, you could do so in my book, Economics of Oil and Gas Production, which is published on Amazon. Check it out at the link in the description. Please take a second to hit the like button, hit the subscribe button, and do not forget to also hit the notification bell. Thank you for watching and goodbye.